let's use what we've learned about surface areas and how to derive them on an explicit function. So what I've got here is I've got a surface that's at a plane. It's a plane, and we know it's a plane because there's no x squared, there's no xy. All of these terms are linear terms. It's x to a power of 1, y to a power of 1, and there could also be a constant that's added there, but that gives us an equation of a plane, no doubt. And we want to figure out just the piece that lies above this little rectangle, or not rectangle, little triangle. If we plot those pieces here, we see that it carves a triangle. And we say, okay, well, what's the surface area of the piece that lies directly above that triangle? And if you recall, our surface area integral looks like this. We take the square root of 1 plus the partial with respect to x squared, the partial with respect to y squared, multiplied by the differential area. Or not the differential area, but the area of the surface may be broken into a differential area. So let's assume we wanted to leave it as a double integral. Usually you can't. But in this case, we're going to be able to, and I'll show you why. So let's go ahead and get our partials. We want to say, okay, well, the partial with respect to x of this function is just 2. The partial with respect to y of this function is just 2. So the surface is 1 plus 2 squared plus 2 squared dA, which is the double integral. Well, that's 4, so that's 9. Square root of 9 is 3. So I have 3 times the area, the differential area. Now, in this particular case, we don't actually have a big issue because what we find is that no matter where we are on this area, the function's constant. It always has the same surface area. So the surface area isn't really a function of the location. It's not a function of x and y. It's just constant. So if you have something that's just constant and is like this, all you need to do is find the area of the actual region, and it's easy peasy. So if we wanted to get the area of that region, we might say, okay, well, that looks like I go from -1 to +1, so that's a length of 2. It looks like I go from 0 to 2, and that's also a length of 2. So I have a triangle with base 2, height 2. Area is 1/2 base height, so the area itself is 2. So my area, or my total surface area, is 6 units squared, whatever your unit is. And so this would be a way to solve this if you have if you have a function that's constant along the whole thing. But generally speaking, we don't have a function that's constant. Generally speaking, we have some sort of function of several variables. So let's go ahead and solve it like we didn't with iterated integral and try to figure out how we would do that. So to go up here, what I see is x goes from 0 to 2. X goes from 0 to 2. But y seems to go from this line to that line. So this line to that line. So what we need to do is we need to figure out what the equations of those lines are. Well, in this one, in this particular case, let's say you start at 0 and you end at 0, 0, and 2, -1. We don't have to consider the z in this case because it's on the xy plane. So if we had 2 points, 0, 0, and 2, -1, we could get a slope, rise over run, right? -1/2. So y equals -1/2 x, mx plus b. In this case, b is 0, is the y-intercept. So it goes from negative 1/2 x. Over here, we have something similar. It goes from 0, 0 to 2, 1. The rise over the run is 1/2. Y is 1/2 x. So now we have our limits for the double integral. So we say, okay, well, from 0 to 2, from negative 1/2 x to 1/2 x, 3 dy dx. Remember, we're doing dy. These are functions of x. Y is a function of x. So we need to integrate with respect to y first. So we get 0 to 2, 3y from negative 1/2 x to 1/2 x. So that's 0 to 2, 3/2 x minus negative 3/2 x dx, which is just 3x dx. Now we take the antiderivative of 3x, we get 3/2 x squared from 0 to 2, is 3/2 times 4 minus 0, 12 divided by 2 is 6. So we end up with the same answer, 6 and 6. Now this one's significantly more work, no doubt about it. So this is why we want to exploit, if possible, if you get a constant value across the whole thing, then you only have to get the area. It doesn't matter if it's a simple triangle or if it could be some sort of complicated region, but if it's constant along the region, if you find the area of the region, it's just that constant value times the area of the region. But and often it's not, so we have to set up iterated integrals. So it's going to be increasingly important that we learn how to define these regions and describe them in ways that are meaningful.